solids have an ordered structure in which there are repeating units. So, for example, you can see this cube here. You can see that it's repeated over and over and over again. And within these repeating units are lattice points, which you can see at the corners of the cubes here. They might represent either atoms or ions or molecules. There are several types of solids. The first is an ionic solid. For example, sodium chloride or ammonium nitrate. Both are ionic compounds. Sodium and chloride ions, ammonium and nitrate ions. So with ionic solids, the lattice points are occupied by cations and anions. You can see a description of it here. Here, sodium is surrounded by chloride to the left, to the right, top, bottom, but also there's a chloride up in front of it here, and there's another one back behind it as well in our three-dimensional structure. And between the negative and positive ions are electrostatic attractions. Ionic solids are hard and brittle. They're brittle in that they break easily. If you were to drop a ceramic plate or to hammer this sodium chloride solid, you would break it because doing so would force all these ions here to the right. And so what happens when that occurs? Well, though you still have some nice interactions between sodium and chloride ions, you now have repulsive interactions between sodium and sodium ions and chloride ions, sodium and sodium, etc. And so it is actually quite unstable to lose the nice interactions, the stabilizing opposite charge interactions, and then to have replaced by them repulsive same charge interactions. So the enthalpy of the system goes from low to high. It's so unstable, in fact, that it's more stable just for the solid to break. And so hammering it causes it to break. Similarly, there's high melting points for these ionic solids. You can see that in our solid, it's a very well-ordered structure with a lot of stabilizing positive-negative interactions. But if you melt this ionic solid, then the particles start randomly moving about, so that soon the chloride particles might be hanging by other chloride particles, and sodium by sodium. Particles might switch places to have repulsive interactions. And so, because that's so unstable, a very high temperature is needed to drive that to occur. So a high temperature is needed to melt ionic solids. They have high melting points. Now, in order to conduct electricity, there need to be either mobile electrons or ions. So ionic solids are poor conductors of electricity and heat. In each of these ions, the electrons are pretty much stuck to those ions. They don't flow about randomly. So there are no mobile electrons. And in our solid, the ions are not mobile. However, if you were to melt this ionic solid, then you would have mobile sodium and chloride ions, and therefore it could conduct electricity. So only if ionic solids are melted will they conduct electricity, or if they're dissolved in water, they can be mobile as well. Okay, so our next type of solid is metallic solids. Examples include copper, iron, sodium. In metallic solids, the lattice points are occupied by metal atoms/ions. Why do we say ions here? Now, originally, though you might have atoms, metals have very low ionization energies. In fact, even at room temperature, the low ionization energies allow for those atoms to give up electrons. And so those electrons will kind of be released from the atoms and can therefore flow about sort of freely between the atoms/now ions. You have a sea of electrons when you have metallic solids. Now, it's still stabilizing to have these electrons nearby. This electron stabilizes both that copper ion and that copper ion. The electrons can essentially be shared among multiple atoms/ions. So that's called metallic bonding. Metals are soft to hard, or they have low to high melting points depending upon the element and / what other elements are with them, aka alloys. They are good conductors of electricity and heat. We can see that here, if you have a positive electrode and a negative electrode, electrons are able to flow freely. They're not attached to any individual atom or ion, so they can flow freely, hence can conduct electricity well, and often the ability to conduct electricity well is closely associated with the ability to conduct heat well. So metals are good with conducting heat as well. That's why we might have a copper pan for cooking. Now, these are malleable and ductile. They can be reshaped if hammered or tried to be put into wires. If you hit this, the ions move, but so do the electrons with them. So there is very little destabilization. The enthalpy is about the same whether the system is like this or like this. It's not unstable to reshape them, hence they can be reshaped without breaking easily. Alloys are metals with other elements combined with them too. We have interstitial alloys in which between the typical normal atoms we have between other elements, like, for example, carbon in steel. Carbon provides a lot of rigidity to the structure because it can bond in a three-dimensional way with all these other atoms. Interstitial alloys provide rigidity by putting small atoms between the typical atoms. We also have substitutional alloys in which iron atoms, say, are substituted by other atoms in the same location that the iron might have been in. So, for example, chromium can allow steel to become stainless. It can be preferentially oxidized compared to iron, so that chromium is oxidized on the outside, not iron, and it can create a kind of protective chromium oxide layer on the outside. These substitutional alloys are not particularly stronger or less strong, rigid or less than interstitial alloys. They remain malleable still. Okay, we also have molecular crystals in which we have molecules like water or long alkanes or sugars. In these, the lattice points are occupied by molecules. Now, molecules only have intermolecular attractions between them. And so, for example, here we see a six carbon sugar bound with another 6-carbon sugar, and it's just hydrogen bonding interacting between the particles. That's not a particularly strong attraction compared to, say, ion-ion attractions or metallic bonding. Hence, the particles can be separated and flow about each other relatively easily. Molecular crystals are soft and they have low melting points. They are poor conductors of electricity and heat because they don't have any mobile free electrons or ions. And finally, we have covalent crystals, aka network solids. They are usually composed of things like carbon or silicon dioxide, aka quartz, or silicon carbide. There's, I guess, two types of carbon that we can see. We can see diamond and we can see graphite. The diamond, you can see each carbon is bound to 4 other carbons in a three-dimensional way. You can see having all this three-dimensional multiple bonding that it is very difficult to break those covalent bonds between the carbon atoms. In fact, it's so difficult to break them that carbon is the strongest known material, and it has an exceptionally high melting point. If you want to melt this, you have to break those bonds, and that means chemical reaction. Not really going to happen. We also have carbon in its graphite form, in which we have carbon bound to 3 carbons instead of 4, and it's in a sheet, one over top of another. So graphite can kind of slough off of other graphite sheets. You'll find this in your pencils. Now, most covalent network solids are poor conductors of electricity, heat, no free electrons here, but when we start talking about having double bonds repeating, we start talking about having a conjugated character in which there is some mild conducting of electricity. All right, thanks for watching, guys.